Hello everyone and welcome to the third video of my Yamaha CS-60 restoration series. There's not much left to do actually. We've done the cleaning and some replacing of chips and stuff like that in the first two videos, and now I've just got the voice cards left to calibrate. But I thought let's do something a bit more interesting. Let's explain how the VCOs work, because we're up to the calibration of the VCOs, so it'd be good to understand exactly how they work before we did the calibration. And also there's just not much information on the internet about these VCOs. I haven't found a lot. I've done a bit of research and I can't really find a lot of information about them. There's a few websites that point at the Yamaha VCO chip and say, look, that's how it works. But no, that's not how it works. It's a bit more detailed than that. So I would like to go into that detail. And let's put some LEDs on the voice cards, because I hate not knowing which of the voice cards is making the sound when I'm calibrating. So I quite often do that with synths. I just put LEDs on the voices so we can tell which voice is active. So we will do that with this synth, and there's a couple of different choices as usual about where to put the LEDs in the circuit. So I've printed out the schematics and we'll have a look at the gate signals and then finish off the calibration. So I hope you enjoy it. I definitely will, because I like discussing the oscillators, especially these ones. They're just phenomenal. They are so different. I'll show you when we look at the circuit, but they're just completely different to all other analog oscillators. They're on a planet of their own. So let's get started. Okay, so this is the schematic of a voice of the CS-50, CS-60 and CS-80. The three are identical except for some resistors which set the range, and that's because of the difference with the CS-80. So there's just 4 resistors up here which set the octaves which need to be changed in the CS-80. But apart from that, everything is identical. So all 3 synthesizers share the same voice board. Now, our job today is to install one of these, an LED. We want our light to turn on when we hit a key and the voice card is active, so we can tell which voice card is making the sound. So we've got to find somewhere to install this guy. Now, let's do an overview of the circuit to understand the building blocks. Now, any analog synthesizer, it's built with the same building blocks as a modular synth. So if you're into Eurorack, you'll be very familiar with these concepts, because you'll be plugging in these individual bits with patch cables, and they'll just have names like oscillator and filter and VCA, which all these circuits do. They're just the same. They're just pre-plugged in. So let's start at the oscillators, and there is a single oscillator in the CS-50, 60 and 80 voice. Yes, that's right, the CS-80 only has 1 oscillator per voice, and here it is. The difference with the CS-80 compared to the other two is that this whole voice block is duplicated. So there's 2 voice layers with a single oscillator each. So I think that the CS-80 is described wrong as having 2 oscillators per voice. It doesn't. It has 1 oscillator per voice, and it has 2 voices per voice, if that makes sense. So here's our single oscillator. It's a semi-discrete oscillator. It doesn't all happen in discrete components, and it doesn't all happen on the chip. The functions that have been split up into discrete and on-chip functions, so they all kind of work together. It's very different to most other analog oscillators. After we generate our saw wave, which I'll explain in a lot more detail later, our saw wave gets converted into a whole lot of other wave shapes. Now, one of them splits off here and it bypasses the VCF, and that's the sine wave. So we get our sine wave come up and go into its own VCA. This VCA just controls the level of the sine wave. So you'll see a slider on the front panel of the CS-50, 60 and 80, which has got a little squiggly line on it for a sine wave. It's in the VCF, it's in the VCA section. So moving that slider just moves the control voltage input for this amplifier, which turns your sine wave up and down in the mix, really. So that bypasses the filter section. Now all the other waves that we've created in our wave shaper, they go into the high pass filter first. So you can see this line that comes from our wave shaper. There's two switches here which switch our wave shapes off and on. So on the front panel, you'll notice there is a button to switch on the pulse. If you press that button, this FET will open and let the pulse into the VCF. And there's another FET here which opens and lets the saw wave through when you press the button on the front panel, and that lets the saw wave in. So this is our input for the high pass filter. Our high pass filter occurs first. They're both in series. So our signal goes through the high pass filter, then comes out our high pass filter, comes out CP2. Now you'll notice it's not plugged in because, funnily enough, the circuits on this board aren't fully patched. There's wires that come off the board and join parts together. So we've got our high pass filter and it comes out CP2, which is a point at the edge of the board. Then there's a wire that comes out of CP2 and it goes all the way into CP7, which is here, and then goes into our low pass filter. So we have our low pass filter, which is exactly the same chip, it's just configured in low pass filter mode. And then we get our signal coming out of CP8. And again, we jump off the board and we come off and we jump into the level VCA for our filter. So you'll notice also in the VCA section, not only do you have a slider for the level of the sine wave, you have a slider for the level of all the other wave shapes coming from the VCF. So this is our VCF slider in our VCA section. So we can turn all those other wave shapes off and just leave ourselves with a sine wave, or vice versa. Then this signal goes into another VCA, but this one is for our modulation. So this takes the LFO signal, which is called sub-oscillator in 1975, 1976. Our sub-oscillator then modulates this amplifier, so we get a really cool modulation of our waves before they get into the main VCA. So after that, we go into our main VCA, which controls our sound level. And you can see the envelope down here, which actually creates our sound profile. So this is our ADSR envelope generator. Now, there's another one of these two, and that is the ADSR for the filter. It's a little bit different because of this IL-AL configuration. So it's not a straight ADSR. That is a conversation for another time. So we have to find somewhere around here to put our LED. Now, unfortunately, the gate signal from the KAS board, which controls our gates for each key, that's actually an inverted signal. So we start at about 8 volts here, and when we press the key that activates this voice card, it actually goes negative. So it's inverted. If we wanted to put an LED here and we connected the LED to ground, the LED would be on when the key's off, and our LED would turn off when we press the key. That's not ideal. We could reverse the LED and maybe get it to work because the signal does go slightly negative. But I don't like putting it here anyway, because as soon as we release the key, the LED turns off. But the sound still might be coming through because we might have a big long release phase on our envelope that still leaves the VCA open. So I like the LED to reflect what the envelope's doing. So when we're on long release times where we leave this guy open, our LED should stay on. So the place where we want to put it is along this line here. This is the envelope that controls the VCA. Problem is we don't have a lot of current spare. I've looked up the chips and we do have a bit. We've got a fair few milliamps, like 5 or 10. So I'm going to use a high brightness LED and use a big resistor so that we don't steal too much current from this line. I'm going to use a 4.7K resistor and a high brightness LED and just take the tiniest amount, which won't affect the VCA. I've already done the calculations and tried it out and it's fine. So we will connect our LED to this line to ground, and then we will get the signal turning on because this is a positive envelope. We'll get the signal turning on when we press the key down, and the LED will stay on when the release is on and we're still hearing sound. So that's perfect. Now, the great thing about this board, look, there's a test point 2 on that line that we need. There's already a pad here, and there's nothing on that pad on the circuit board. So we can put our LED into test point 2, solder it on the other end with a resistor to ground, and we're done. Okay, here's all my LEDs. There are 7 of them here, and they're all finished, and I will show you how to make one. So just a big long wire, any old wire. I'm using a 4.7K resistor, so I don't grab too much current. Doesn't really matter the value. I've just chosen the highest one I can to make sure the LED turns on and I can still see it. You don't want to go too high that you can't see the LED anymore. I've just chosen any old high brightness LED, and we're going to connect the resistor to the negative end. If you have a look at LEDs, they have a big side and a little side in the middle. The big side is usually the negative, and that little side on the long leg is positive. So we'll go positive into test point 2, negative into our resistor, and then I'll just find some place to connect a ground on the voice card and figure that out later. Right, and our first LED is in the board. You can see it here. Test point 2, it's hard to see now, the LED's in the way, but it's labelled on the board. You can see it there. I've just put the positive leg through test point 2. You can see it sticking out the other side. I haven't chopped it off yet. And then we've got the resistor, which is under the shrink tube. Don't forget the shrink tube. And then just a wire that goes to ground. There's a big ground point at the main corner of each board. There's a huge set of pads where those screws are. That's all ground. So I just connected it there. And let's turn it on and do a test. Right, so the first key that I press will activate the first voice card, which this is. So there, and you can see the LED. Woohoo! So we should be able to see that LED when we're looking in between the voice cards, and that'll help us find out which voice card it is. So if I press the same key again, it'll move on to the next voice, and that LED will go away. So again, and it's off. And I'll have to press it another 7 times to get back to voice 1. There we go. Now, again, with this synth, we won't activate the 8th voice card unless we're pressing 2 keys at a time. Right, so that's done. I'm going to go and install the LEDs on the other 7 voice cards now, so we have all 8 done. Okay, so the LEDs are installed, and I've turned the lights off. And yes, in case you're wondering, it is perfectly normal to be in the dark with your synthesizer. So I've just done it to make it easier to see the LEDs, of course. So let's start with voice 1. Oh, it's not even on. Hang on a second. Here we go. Oh, that's nice, that orange light. And look, if you have a look at the end, we've even got the pretty light from the keyboard, from the aftertouch. So, okay, should work now. Voice 1. Yep, we got it. So it depends a little bit on what angle you're on, because there's a lot of components and wires and stuff in the way. So number 1, 2, 3, 4, 5, 6, 7, and to get voice 8 I need to press another key at the same time. There, perfect. Oh, look at that, pretty lights. Christmas tree synth, yeah. Okay, so that's a success. So we're done with the LEDs, and I might go through how the VCOs work now before we do the calibration. Awesome. Okay, so this is the schematic for the Yamaha VCO, and this VCO was used all the way from about the mid-1970s, 1976 when the CS-50 came out, and a year later the CS-60 and CS-80 came out, and that was used all the way through the black models like the CS-5, CS-10, and all the way through the ones with the wood side panels, which are like the CS-20, CS-40, and then ended up with the CS-70M. To explain it and how it's different, I'd kind of need to draw out all the oscillators. I'm going to avoid doing that though. So there were 3 main types of analog oscillator. The first, like Moog, ARP, or the SEM, the Oberheim, they were fully discrete. They were probably known as the best oscillators or the best sounding. So the early Mini Moog, the ARPs were fully discrete, and the SEM and the OBX, they're all known for being really full and rich and a little unstable. After that, we went through a period where ICs were used to support the discrete components. So we would start to see op-amps and comparators and things like that to support discrete components like FETs and transistors and switches and stuff. And they were the main types. So that's like the Jupiter 8 and the later Moogs and heaps and heaps of oscillators. All the VCOs were based on that type of design. And they were probably the most popular. And then by about the mid to early 1980s, the whole oscillator just went on the chip. So that's when you see oscillators like the CEM3340 just dominate. And none of these components or parts of the circuit were external or discrete anymore. They were entirely on one single IC. And from that point onwards, really wasn't the same ever again. And then we saw the digital synths come along. So out of all those different types, this VCO really doesn't sit anywhere. There isn't a design that's like it. This is the most unique out of all of them. Firstly, not all of these components are in the IC. In fact, a lot of them aren't, and it's very confusing which one's which. So I'm going to circle them. So firstly, we have this op-amp and transistor that's on the IC. We have the constant current source and the switch, which is on the IC. And we have this part of the circuit here, the comparator and the pulse. So what happens is, firstly, we need to fill the capacitor. So this switch is closed, and that's controlled by this comparator here. So we won't explain that just yet, just that the switch starts closed. When this switch is closed, we get current coming from this constant current source, filling the capacitor, and we get to our starting position, which is at the top of the saw wave. Then this switch opens very quickly. It's only held closed briefly because of this pulse. And the timing of how long that pulse is controlled by this circuit here. So the timing of how long this switch is closed, we can control. That's one of the calibration parts of the circuit. Doesn't really matter too much. We just need to close the switch briefly enough so that we can charge or build up enough charge in this capacitor to start the process. Then switch opens. We start draining this capacitor through this transistor here. So this is the part of the circuit that controls the frequency. So our input voltage comes into this op-amp, and this transistor, which sits in the feedback loop of the op-amp, controls, it's sort of like controlling the resistance through here. We're actually controlling a voltage drop. So the voltage is built up in here, and we're controlling a voltage drop which goes across these resistors, which drains out to ground. So this transistor controls how fast this capacitor drains and how fast this slope is. So the faster we pull current out of the capacitor, the higher the frequency. Now, the really great thing about this, because the keyboard in Yamahas and Korgs was hertz per volt, so exponential keyboard, is that we don't need a conversion circuit out here to convert between 1 volt per octave and the exponentialness of our oscillator, because the keyboard is already exponential and the oscillator is already exponential. We don't need a conversion between the two. So the key input voltage just goes straight into here. So immediately we cut out one of the most common sources of drift in all oscillators, and that's the exponential converter. It's just a nightmare. I may do a separate video explaining that actually, because they're quite interesting, but we don't need it. So straight away, this oscillator should be more stable than all synths that are 1 volt per octave compatible, because we don't need that exponential converter and we don't need all the compensation to stop it from drifting with temperature. Now, there's another part of this circuit that I'm most impressed with, and that's the way that it changes the keyboard scaling. So if you look down here, in the line where we drain out to ground, there's a resistor here. On the actual voice card, this is a set of resistors, and they're selected by a set of FET switches. And these resistors are what control the keyboard scaling. Because if you have a think about it, if we want to change the current draining out of the capacitor, all we have to do is change this resistor. So if we change this resistor by double or half, we will double or half the frequency of our oscillator. So if we want to go up an octave, we just make sure that this drains out twice as fast. If we want to go down an octave, we just make sure that it drains out half as slow. So the great thing about that is we don't have to change our range. We don't need a huge linear range for our input control voltage to change the keyboard scaling. All we do is keep the same range, the same width of the keyboard, and we just change the resistors at the bottom to shift the pitch of this whole thing up and down. So the great thing is we don't have to change anything here. We just change the resistors at the bottom, and they're just switched in and out by a set of FET switches that are controlled by the up-down octave buttons on the front of the synth. So that's just brilliant, because also once you set up these resistors and you've calibrated them, they never need to be changed again, and they're not going to drift. So that's awesome. Right, so moving on, a little bit about how this comparator works in this part of the circuit here. So basically the comparator just helps us decide when to turn this switch on, which brings our voltage back up to our top level. So we decide when we want to charge this capacitor again. So we're draining out, and at some point we reach a certain level and we want to fill the capacitor again. So this FET really just tracks this voltage that's in this line, so we're monitoring it going down, and when we get to a certain level, this is like a positive voltage, by the way. It's not written on here. I think this is just the normal positive rail, and so this FET lets in voltage into this line, and whenever it gets to this threshold, it's triggered again, and the comparator fires off this one shot here, which closes the switch and charges the capacitor. So it's really not that complicated. Where it gets interesting though is that because we've got a constant current source here, this circuit sort of has a built-in Achilles heel, or it's kind of got a built-in fault, in that normally in other oscillator designs we short this capacitor out or do something to charge it up really quickly, like instantly, to get that first part of the wave or the end part of the wave where we chop it and short it out. That part has to happen really quickly to get our saw wave sound. If this part charging is delayed, we end up with a triangle wave, and that doesn't sound anywhere near as bitey. There's much less higher frequencies. And the problem we have here, because we've got a constant current source, this doesn't short out instantly. There's a finite time that it takes for it to charge up, because we're only letting in 800 microamps. So this part here, this constant current source, ensures that we never actually get to charge this capacitor instantly. There's always a little bit of a delay before we discharge slowly. So the waveform here, the shape that this oscillator generates, is not our saw wave. There's actually a little bit of a slope on the front. Now the problem is that's not a saw wave. And so this part of the circuit here is like a mixer, this wave shape converter. All we're doing is mixing in part of this pulse that we generated, and we're mixing that over the top of our distorted saw wave to make it more like a normal saw. So what we're doing is we're actually adding a saw at the front of our misshapen triangle so that we get more of a square shape. And that's described down here. We actually mix these two together. That's why the saw wave in the Yamaha oscillators have this little glitch on the front. And that's the one that Roman was talking about when he was designing the oscillators for Deckard's Dream. He was describing how he was able to recreate that to make it sound authentic. Right, so that's how the oscillator works in the Yamahas. It's very, very interesting. Really great positives about it. Not much drift because we don't have an exponential converter. Octave changing is really, really easy. Sort of doesn't look like a falling saw, but whatever, we get around it by adding a pulse at the start. By the way, this falling saw is not actually what we hear because then it goes through a wave shaper where it gets converted to a rising saw, which is a bit disappointing because falling saws sound better. And also, if you think about it, the level here, we're actually drifting down, discharging. So we're coming down to 10 volts, reaching 10 volts, and then triggering the switch again. So we're actually moving from about 13 volts to 10 volts. So this has quite a big offset. So it's another thing that the wave shaper chip deals with next. Right, so hope you enjoyed that. That's how the Yamaha oscillator works. Now let's move on. And finally, I get to finish off the calibration of this synth, which I've been waiting to do for ages. Okay, so before carrying out pitch adjustment, be sure to stabilize electrical circuits on your synthesizer more than 10 minutes, blah, 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 blah. Yes, it's been on for ages. Adjust the following variable resistors. So when tuning knob panel is in center position, we've already done that. We put that in the second video, we put that in the center position, and we did some adjustments on the KAS board. But this is different. This is on the sub board. So we're monitoring the voltage still in the same spot, which is that TU terminal and earth on the KAS board. Now I originally had this at 4 volts, but it has changed a little bit since we did some other adjustments, and it might have been the adjustments we did on the sub board. So 3.97, we have to adjust VR14, which is here. So that says 4 volts, and it's very touchy. Like, see, that was enough to put it way over. I hardly moved it. Oh, okay, that's it. I'm going to leave it like that. So, 4 volts, back to 4 volts. Number 2, short circuit terminals EK19 and E12 on M circuit board when tone selector is set to flute. Right, so it looks like we're finished on the sub board. I'll put the sub board back. We'll bring out the first M board for voice 1, and we'll do this second step now. Okay, step 2, short circuit terminals EK19 and E on the M circuit board, so that's already done. EK is this black wire coming in here, and I've just used a parrot clip to short circuit that to E, which is ground, and I'm just using this edge connector. The bottom edge connector of all the cards is ground. And we're measuring here on CP6, which is pin 5. It's not very well described in the manual. It actually tells you, just says CP and then 5 in brackets, which is pin 5. I've had a look at the schematics, and it's definitely this one. Now, I couldn't get my probe on there, so I've had to solder in another wire into CP6 so I could connect my probe to it. So what we need is this one to be 0. This pot here, it's very touchy. Mine was a little bit out. It was originally minus 1.7, and that's as close as I can get it because I've tried a few times already. So that's done. That's just the 0. What I'll do is do that for every single one of the boards, then put all the boards back in, and we'll do the tuning, because the tuning, the pots can get accessed where the cards are in the instrument, so you don't have to pull them out. There's a whole lot of test points and things that you're supposed to use a frequency counter for, but I never do that. I'll just use the tuner on my iPad, and then I'll beat match between the voices. So I'll put the cards back in after I do that 0 on each one, and we'll do the tune. So I finished the 0 calibration on the 8 voice cards. Some of them were quite far out. I think voice 5 was 5 millivolts out, and I had a couple that were around about 3 millivolts out. Most of them were between 1 and 2, but to have a few cards that high was quite an issue. They're supposed to be within 120 microvolts, so that's 0.1 millivolt. So to be 5 millivolts out that's way out. Right, so finally up to the tuning. Yay, the fun part. It's only taken me 2.8 videos. So I've got my iPad, which is tuning my voice at the moment. So here we go. 3. We're checking the output frequency on the 9th pin, blah, blah, blah. I'm not going to do that. VR3 to have a certain highest note. Right, so CS-50 and CS-60. So we're looking for C7, which is the top note on the keyboard. And we just want to tune it, really. And the pot that we use is the really fine tune, the 25 turn fine tune pot. The only good pot they put on these bloody voice cards. So we use that one to set our high frequency C7. So here we go. C7, pressing C7. Voice card 1 is on. We're flat. Okay, so I've had to take the iPad down and put it closer to the speaker so that it can tune on the high frequency a little bit better, but it's correct now. So I just have to keep doing that with all the other voice cards and adjusting the same pot. So all I'm doing is just pressing the key over and over again and looking at where the LED is and just seeing which voice is out of tune and just adjusting that pot. And it's a lot easier than you think. So just press the key. At the moment, the light's on voice 2. That's in tune. 3's good. 4's perfect. Good. Good. Bit sharp. Pretty close though. Okay, so the first 7 are done. So I need to stop at 6. Then press the note before C7, because I can't press C7 because I need to press it at the same time as another key to get it on voice 8. So I'm pressing the key before C7, and at the same time I'm going to press C7 and then let go of the key before. Okay, great. Flat. Perfect. Right, so now we're up to the second part of number 3, and this is where it starts to get really confusing, and we find out that the notes here are actually written wrong. Let me explain. So we've just done the first part of 3, which is that high note. Now the second part and the next 3 parts are actually sort of the low range. Not really. What we're actually doing is changing the keyboard scaling resistor that we switch in and out of the VCO. Remember how I talked about the VCO, and there's a resistor at the bottom here which helps drain out the capacitor, which sets the octave. So you've got 4 resistors here and they're switched in and out by a FET matrix. So each one of these resistors that gets switched in and out of the bottom is for a different keyboard scaling, and they relate to these switches at the front of the panel, right? So there's our 4, 1, 2, 3, 4. So what we're doing in the second half of 3 and the next 3 steps is we're calibrating those resistors, and there's 1 on each of the boards, and you can see these 4 big pots that are on the top. Now, we're supposed to start with 1 octave up, but all of these notes here are actually written for the normal scale, which is next, which is 4. But we don't do the low range of the keyboard. See how it's written here, C3, C2, 3. We don't do that for normal. We actually do it on C6. The next 3 steps, we actually hit the C6 key, and we do C6, C5, and C4. This one we're supposed to hit the lowest note on the keyboard and do 1 octave up. So this is a C7 to C2 keyboard, 5 octaves. If we hit the lowest note, if we hit the lowest key at C2, we get C3 when we're 1 octave up, see? And here, C2 to to C7 keyboard, it's telling us to hit C1. It's wrong. And 1 octave up, that would be C2, but it's not, because we have to press C2 and it ends up being C3. So what complicates this a little bit is that I didn't do the first part in 1 octave up. I did it in the normal position, and I did use C7. In 1 octave up, that would have been C8. The reason why I did that is because the iPad can't pick up C8. So when you use a tuner, you can do this first part here, normal, and you can do it on C7, because this isn't part of the octave of the keyboard scaling. You see, it's from this part, this part, this part, this part is the keyboard scaling. So you can really do what you want at the top. But now we have to do it correct. So I'll show you how to do that now. Okay, so to do the calibration, quite easy. Let's see, 1 octave up. The manual says hit C1 and tune on C2 because we're an octave up, but C1 would be here on the keyboard. It's a C2 to C7 keyboard. So we hit C2, and because we're 1 octave up, we tune on C3. Now that will be different with every voice. You will need to cycle through every single voice and check. That one's a bit low. Oh, it's voice 1. You need to install the LEDs. Trust me, you just need to install the LEDs. Now I've lost my voice. Where am I? 1. That's it. And you just do that for all the voices for each step. So the next keyboard scaling is normal. And then we switch to the C6. And you do that with all 8 voices. C6. And then you do 1 octave down. Same C6, but now we're tuning on C5 because we're 1 octave down. All 8 voices. And the same, 2 octaves down. That's it. Okay, right, we're up to number 7. After all that, actually, I don't want to freak you out, but I did the entire thing twice over because the second time it's always ever so slightly different. But my tuning is sensational now. So number 7, we actually adjust the whole tuning for A 443 Hertz. Now my A may be 440. What I've done is I've used my iPad for everything. So I'm going to continue to use my iPad when I tune for this A3. If you use the frequencies, follow the frequencies. If you use a tuner, use the tuner. Don't mix and match. So A3, which I think is the A near the middle of the keyboard somewhere. To double check, make sure you're on normal. Because when you're on normal, you'll get the real A440 or A443. So ready, press. Wow, that's close. That's really close. I may not even do this adjustment. It's just on that subboard. And it's VR14. Where are we? CS-60, VR14. Adjust to get A. But it's already in tune. So I think I'm going to leave it there. And we're done! Yes! We've done the whole voice calibration. That's awesome. We can go back to the normal part of the manual. Okay, so we're back to the service manual for the CS-60. In the adjustment section, we have just done number 1, pitch adjustment for the M board. Yes, all that stuff we just did was number 1. Now, number 2, the envelope generator circuits. I'm going to leave them as they are. They sound okay. If you've got a digital oscilloscope, a storage oscilloscope, you can do them if you want. Mine sound okay. I have bigger fish to fry though, and I really, really want to get to the filter calibration because this is what really defines the sound of the synth. Besides it being in tune, which determines whether it sounds horrible or not, whether it sounds great or not, depends on these. Because I quite often set up relationships between the filter cutoff frequency and the oscillator frequency. So I'll sit one of the cutoffs on an octave higher above the oscillator or something like that. And I like to maintain that relationship throughout playing chords, because if one of those voices is slightly out, the entire tone will change. It's like you're playing a different patch. So this really has to be calibrated really well. I've got a different way of doing it Here we're told to use a square wave and listen to the difference between the cards in the cutoff and try and adjust the cutoff so that it matches all the other cards that we're listening to. It's a little bit hard to do that when you've got an oscillator also at a certain pitch. So I like to use the noise. So instead of using the square wave, I use the noise, and then I do the same settings for the sliders, which I'll show you, and I put the resonance up really, really high. In fact, higher than what it says here. So in that manual, we're told to put the resonance sliders up max. So the first one we're doing is the high pass filter. So we put that halfway. Resonance sliders up max, but what it doesn't tell you to do is move the global resonance slider up. So up, if we use the paddles and put them in the up position at 0, if we move the paddle down, we actually get twice the resonance than we had when we just put the slider up. So this is like half the resonance possible on this synth, and moving this down would be the other half. So I increase the resonance, make sure you have the filter, global filter cutoff on halfway, where the notch is. We're going to do the high pass filter first, so that's halfway. And I've got the noise up, and I've turned the oscillators off. So we'll just listen to the noise difference between the voice cards. Now, that will sound something like this. And we are supposed to tell the difference between them and then calibrate. And what's worse is the pot is right underneath. But if you listen carefully and if you do this yourself, there is a definite difference between some of these cards. Now, I'll turn this up a little bit and try and see if you can hear the difference. That one's higher. Higher. That one's definitely higher. This card is higher. If I go between these two, they're very, very similar. When we go to this one, you can tell that it's higher. So you can tell the idea of what we're supposed to do. So I'll do that again. We'll have a look at the LED on these two voice cards, which sound the same. Then listen for the change with this one. Yeah, so I'm going to pull that card out now and move the, where are we? What are we supposed to do? Adjust VR7. So I'm going to adjust VR7. Okay, so I've pulled out that number 7 voice card that had the higher sounding high pass filter. And VR7 is here. So let's have a listen again. Yeah, it's higher. So I'll turn it down. Try that. Oh, that's close. So now all I have to do is find all the other ones that are like that. Okay, so I've finished with the high pass filter calibration. They sound a lot more consistent now. I'll just show you. So that's much better than before. I've tried that using different keys on the keyboard because our keyboard is tracking our oscillators. That is done when these two sliders, the keyboard control brilliance, are in the nominal position, so where the line is. So if you leave it there, it's equivalent to the other synthesizers 1 volt per octave filter tracking. So basically that just says we're tracking the oscillators. So when you change keys, you change pitch. And you can do that over and over again, different pitches, to see if you're still calibrated. Now, we're up to the low pass filter. So low pass filter goes to halfway. The high pass filter goes fully open, which for a high pass filter is down. I don't know why you'd need the resonance still up. The manual says leave them up, but that's wrong, really. You should only have one of the filters active. So now we're doing the low pass filter. Noise is still on. I have tried with the oscillators, and it's really difficult to tell the difference between the filter cutoffs because the oscillators gets in the way, especially if you use the pulse, because we haven't calibrated the pulse width yet. And different pulse widths can sound like different filter cutoffs. So whatever you do, don't use a pulse. Let's leave it off. Noise is good. Noise is working good. So, low pass filter. We're going to tell the difference. So I'll pick a higher key. Little bit of difference between some cards, nowhere near as much as what the high pass filter differences were. So it looks like we're getting close to finishing the calibrations. Okay, so finished the low pass cutoff adjustments. And I thought of a better way to do it, and I've got much better results too. So firstly I did the noise, I got them pretty close. I decided to check by using the oscillators and notes and stuff. But the way you do it according to the manual, where this slider is halfway, honestly I can't tell the difference between most of the notes when the oscillators are on. It's much easier to use a noise. So I thought, well, but what if we use an oscillator and we put the filter cutoff to resonate at the same frequency as the oscillator, so they should reinforce each other and produce a louder note. And when you move the cutoff away from that fundamental frequency, they'll no longer reinforce each other and may even cancel each other out and get softer. So I tried it and it was brilliant. It works awesome. So I'll put the camera on a stand and I'll move the cutoff and I'll see if you can tell the point where they reinforce each other. And then I'll show you what happens when I adjust one of the cards to have a different cutoff and it no longer reinforces, and you can hear the volume difference. It's amazing. Right, so maybe this note. Now, if we go all the way past, we pretty much cut off most of the note. As we go up, there'll be a point where it's loud, and if we move away, it gets softer again. So all we have to do is scan that range and find the loudest point, and we've hit the right position in the cutoff. Soft. Loud. There, so that's the loudest point. Now, okay, so let's demonstrate what happens when we move one of the voice cards away from that point, and you'll hear the volume drop. Well, hopefully you will. I can definitely hear it from here. Try this one. Now, I'm going to move the pot with the board in place. Don't do this at home because you might short everything out. You can use insulated screwdrivers, which are awesome. Some of these pots are still hard to get to. Right. I'm going to stop when this voice card LED turns on. There. Now watch what happens when I adjust the pot. It's VR9. Watch what happens when I adjust VR9 away from the fundamental frequency. The volume drops. Can you hear the difference? Now I'll scan past it again. Hear how loud that is? All I have to do is get the cards to the same volume and I'm at the right point. Awesome, much better. Okay, so I've gone and now recalibrated the high pass filter using the same method by finding the frequencies where the filter and the oscillator constructively affect each other. And that's just so much more accurate than anything that was in the manual or that I'd come up with previously. So both filters are absolutely spot on now. And I've tested it by using things like the ring modulator frequency, oscillators, and the filters all kind of in places that are really important to tonality, and small changes can make big differences. and just playing the voice cards over and over and over with the same key, and I should get exactly the same tone. And it's just the best it's ever been. Wow, there's no difference between voice cards. It's amazing. Okay, I have to try and not get distracted by playing the instrument. So close now. Okay, so VCA circuit. This one can be done with just using the tops of the board, so we don't have to pull any of the boards out. And what we're doing is just matching the level of the sine wave that bypasses the filter section with the output of what goes through the filter. So if you look at these two sliders on the front here, the VCA level and the sine wave level, they have to be balanced between all cards. Or when we play voices, one of them might have a slightly higher sine than the other voice, and we'll notice differences. So they need to be the same on each voice card. It doesn't really matter what they are, they just have to be the same. Now we get a good guide, which is 1 volt peak to peak and 800 millivolts peak to peak. The test, actually, it's done on CP4, which is 28. We can access it via the top. I will show you. I'll put my probes on, and then we'll use the oscilloscope and we'll do the calibration. So here's the probe. I just have ground on the ground rail here. And CP4 is between the yellow and the purple wires, and it's labelled CP4 on the board on this side. It's easiest to get the probe to stay on the solder pad on the opposite side of the board. There's a hole on this side, but it's difficult to get the probe to stay in the hole, so I connect it touching the pads on the other side. What we want to do is put the sine wave slider up to full, because we're doing the sine wave. Now we're adjusting the pot that's in the middle, well, sort of. There's 4 here and 5 on this side, so it's this one here, that pot. And we adjust that pot so that we've got 1 volt peak to peak. Now I've got the 0.5 scale now, so it's 0.5 towards the bottom and 0.5 towards the top. So 1 volt peak to peak would be between this line and this line. So you can see it's outside of that range. So if I move it to 0.2, it should be 0.2, 0.4, 0.5 is here, this dotted line. So I need to get the sine wave within the dotted lines. And I just do that by adjusting this pot. Oh, that's really touchy. That moves quite easily. So you can see that's about right now. But even the slightest movement sent this sine wave off the chart. So as with most, it's very touchy. So you just have to do that with every voice card with that middle pot until the sine wave is exactly 1 volt peak to peak. Okay, so the next is the output of the filter section. So we have to turn the sine wave down, turn the VCF level up, and we don't want the resonance. We'll just have a look for a normal wave. So we'll turn everything down, high pass filter up, pulse on. So now we should have a square wave. Oh, there's a little bit of resonance still there. See, look, I'll show you. See how you've got, oh, focus camera. Yeah, see how you've got that little squiggle at the start? There's some resonance, and I think I know where it is. It's the master sliders, they're still up, so resonance up to 0. That's better. It's more like what it should look like. It's not an exact square, but the CS-60 is a special synth that has special waves. Right, so we need to get it to about the same level, and this one is nearly, it's just a bit short. The pot that you want to use for this one is the next one up. So, yeah. Yeah, I think that's about right now. So that's done, and again, you do that with every single voice card. So change your probe to the next card, adjust the pot on the next card, and do all 8. Okay, the next adjustment is actually really important. It's the level of both waves together at the point where they're mixed. And there's a mistake in the manual too. So in number 1 of the VCA, we've adjusted VR11. Number 2, we adjust VR12. Number 3 should be VR13. It says VR3. If you touch VR3, you'll throw out the tuning for the whole card. VR3 is that blue one we adjusted at the start, and that's a pain in the butt. So VR3 and VR13, sorry, and if you look where it is, we're adjusting this VCA here. There's actually 4 VCAs on the output, which is amazing. One we adjusted, which was for the sine wave level. We've already done that. Then we adjusted the output from the filter. We've done that one. Now where the two are mixed together, so we're doing this one, and this is where the modulation occurs from the LFO. And then we've just got one more left to do, and we're done. Thank God. So, right, so we put our probe on a different pad this time. It's actually CP5, so, and it's right near the top. You'll see it labelled on the board. It's very hard to show here, but my probe is on a pad that's between the white wire and the brown wire. It's hard to see. So, and then we just adjust for the same level that we saw before. So it's exactly the same wave because we haven't changed anything, and we just need the same level. So this one's quite low, actually. So we've finished 3 out of the 4 VCAs. We've just got 1 to go, which is the last one. So this one accepts the control voltage input from the ADSR. So to do the gain, we need to have the sustain up at 100% and be pressing a note down, and we monitor the output. Now the instructions are again confusing and a little bit wrong. They don't tell you where to monitor, so it's easy to just keep going with the one we were using before, but you won't see any difference because we're actually doing the output of this VCA, and the one we were previously using was monitoring the output of the VCA beforehand. So nothing we adjust here will make any difference to this one, CP5. So we need to be monitoring this output. Now that's pin 33, well it says D here, but in the layout it's O for output. So there's a mistake. That one is easy to find. It's just the white wire near the top of the board. So the brown ones at the top, they're positive. They're the positive voltage. It's this white one second from the top that we need to monitor. I've got my probe on there now. Well, it's very hard to see because I have a black probe. There, so I'm monitoring this white wire. And remember those conditions. We need the sustain high at 10. And both the level sliders should be up, obviously. So I must admit I had trouble with this calibration. You get a lot of crosstalk between the channels because this is the point that they are mixed together. So when you press a key to open the VCA, make sure you look at the LEDs on the voice cards so that you're monitoring the voice card that you're calibrating. Otherwise, the levels won't be correct. So hit a key, look for the wave on the screen, get the right level. It's about 0.24 volts for the CS-60 and the CS-80. It works out about right, but I must admit it was difficult. And the last one is pretty easy. You just put the slider down and make sure that nothing gets through. And if you see a signal get through, you adjust the pot at the very top. So that's it for the calibration. Oh my God, it's taken so long. Awesome. I'm going to put it all back together now and put the screws in and never open it ever again. thanks for watching. It's been a really long one, about an hour long, but I hope you've enjoyed it. I've definitely enjoyed making it. I found out a whole lot of stuff, particularly the calibration of the filters, and the way I did that, matching it to the oscillator frequency, the fundamental frequency. I found that just brilliant. Wow, that's it. Finally, I can move on. All right, see you in the next video.